And with that, I would like to introduce our first speaker, Fraser White, who will give us a brief introduction on high pressure crystallography. Fraser?
Thank you, Joe. Let me just arrange my screen properly. Okay, so thank you for the introduction. I just wanted to introduce myself and my high pressure credentials, if you will. So my name is Fraser White, and I'm currently the product marketing manager for Rigaku Oxford Diffraction. My first brush with high pressure research was back in about 2004, when I started my PhD on a completely different topic, but I was embedded within a group of people who were doing high pressure research every day. So I don't consider myself to be an expert, but that naturally at that time made me want to learn a little bit more about high pressure and try to do some of my own. I didn't do anything too serious, but I did participate in a few trips to synchrotrons, processing data and collecting the data. And then after Edinburgh, I ended up working in the company, and there I was doing demos for customers who were doing high pressure research. So over the course of about 15 plus years, I've been involved in high pressure research in some form or another. Okay, so next, who is this workshop for? So this is really an initiative from Pierre. A few months ago, he realized that we had a number of users who were interested in high pressure, but didn't really know how to get started or what they could do with it. So in the first place, this workshop rather was intended for those people. So if you've never done any high pressure research, we hope that here we can cover the basics through to some more advanced topics. So if you've already started in high pressure research, there will be some hopefully useful information here for you as well. And if you've done high pressure research on other vendors' instruments, then again, hopefully you'll see how things work in our side of the fence and be able to translate those ideas across and use our instrumentation. So I hope not to tread on the toes of my colleagues and our invited speakers too much during the course of this presentation, but my job here is to try and give you a flavor for high pressure research and what it can be used for. So let's start by defining what we mean by high in these high pressure experiments. So I have a picture of all of our home here, and in our atmosphere, the high pressure is very modest next to these experimental pressures. So standard atmospheric pressure sits about here on this exponential scale. And this is the standard atmospheric pressure. The highest pressure ever recorded in the Earth's atmosphere is about here. So that's a very, very modest increase, but this has some quite drastic effects on our weather and how we experience the pressure. So without us deliberately applying any pressure to a sample, this is where somewhere in this range down here is where we'd be collecting almost all of our crystal structures. So obviously atmospheric pressure does vary a little bit, but generally we consider not really any change whether you're at this pressure here or this high pressure here. So what about other measures of pressure? So the highest pressure recorded on the Earth or under the ocean is here. So this is in the Challenger Deep in the Mariana Trench. And this is about 11 kilometers below sea level. So if you're into diving or anything like that, you'll know that every 10 meters of water increases the pressure by 1 atmosphere. So at the deepest point here, we have something like 1.1 times 10 to the 8 pascals. So next step up the ladder is the center of the Earth, and here we have 3.3 times 10 to the 11 pascals, so that's quite a large jump there. And this is starting to get to the kinds of pressures that we're looking at now for our high pressure crystallographic experiments. So this happens to be the highest man-made pressure. So this is someone doing high pressure X-ray diffraction experiments, and you can look this paper up here if you're at all interested. But this is the highest recorded pressure that I'm aware of, and I may be out of date or wrong on this, but this is sitting around here. So you can see where our experimental pressure range is. And just for the sake of completeness, since we have the sun in the picture, the center of the sun, the pressure is estimated to be something like 2.65 times 10 to the 15 pascals. So that's a very large step up there. So our topic for today and tomorrow is high pressure research, and that's all taking place within this kind of range here. So going from atmospheric pressure down here up to this highest recorded pressure of 7.7 times 10 to 11. Most of these high pressure experiments will be in the top half of this because we generally are not going up in such small steps here with the equipment that we use. So why would you want to study with high pressure in the first place? So this is a few graphs I've put together to try and explain what it can do to your structures. So when we talk about temperature, which you can see in the top graph here, there is a similarity to high pressure. So there are plenty of reasons why people use temperature in crystallographic experiments. And I'm sure that a lot of the people in the audience, if they've not done high pressure, they probably have done something with high temperature or low temperature or somewhere in between, and doing a range of the structures across these temperature ranges. And you'll know that changes the phases and things like this of this structure. So the same is also true for pressure. Often the reason that you'll do it is simply because you want to explore those phases and the changes. But the long and short of it is that pressure can give you a degree of control over the structure and the packing. So it has a similar effect on the cell parameters as temperature, but it would be wrong to say that they're the same because one is removing energy from the system and the other one is adding it. So what I mean by similar is that decreasing temperature will generally reduce cell dimensions just the same way that applying pressure will. It's probably not that surprising to you that if you squeeze something, it will get smaller. So these graphs here show you that there's a general downward trend when you increase pressure, and the same again with reducing the temperature. So when comparing the changes in dimensions, you can see here that the whole of that temperature graph fits roughly into this region of the pressure graph. So for this example here, I'm using some data on benzene, which is found in the CSD. And there's even actually a point out at 24 GPa on the CSD. I should, for the sake of correctness at this point, say that the data points in these graphs are not all from the same authors, so you should take this with a bit of a pinch of salt when you're looking. There may be variations in the way that the experiments were done. But I'm only really showing you this to illustrate why what the differences are and how the rate of change is different for using temperature and pressure. Okay, so examples of the physical properties changing under pressure are shown here. So this was from last year. I think it was in October that this paper was published, and someone has been able to use pressure to achieve room temperature superconductivity in a material. So I've included the link for that here if you want to get it, and we'll put the slides up on the forum after this, so you'll be able to click on it if you don't want to copy it down just now, because it's not a very friendly link to look at. But this is just one example. There are lots of things that you can do with pressure, so I've listed some of the things that I could think of off the top of my head here. And you can do things that you can't do by other means, like crystallizing gases, for instance, or liquids that don't freeze when you go down in temperature. You can study the effects of these changes on the structural, the functional properties of materials, for instance. So let me remind you at this point that we will have a talk tomorrow at 10:15 Central Time from Professor Boldareva and Dr. Zakharov, and that's on some of the applications of high pressure research. So we will cover that in the program of this workshop. So now that's the what and the why. So now for the how. So how do we get to the gigapascal pressures that we typically do these kinds of experiments at in a way that also lets you conduct a diffraction experiment. So people who are unfamiliar with high pressure crystallography experiments might think about large pieces of industrial equipment like this. This is a reactor used for the Haber process in around 1913 that achieves something like 200 atmospheres. So that's a very modest pressure when it comes to the types of things we're doing our crystallographic research at. You can see that there's a person down here in this photo, just to give you an idea of the scale here. So obviously something like this was being used to produce chemicals on an industrial scale, so it needed to be big for that kind of reason. But for our purposes, getting to pressures is actually quite easy. So this is to demonstrate that point. So what we're doing here, we have a weight sitting on a cone. So when I say low pressure and high pressure, I'm talking about the pressure exerted on this tabletop by the cone here. So if we assume that the cone itself is weightless and we're just pushing this 1 kilogram weight down onto the table, by flipping this cone over, we can have a drastic effect on the pressure that is exerted on the table. So when you look on the left situation where we have a large area sitting on the table, then we only apply 10 pascals to the table. And on the other side, where we have the cone sitting on its point, we have 10 megapascals of pressure on the table. So the only change here is flipping this cone over. Everything else is the same. So that's telling us that all we need to do to be able to reach these high pressures for our experiments is to miniaturize everything. So the devices we use to do that are called Diamond Anvil Cells, and you can see in the little animation here how they go together. So we have our crystal sitting on the face of a diamond, which yeah, you can see there. So I'll show you in another slide in a second what that looks like more slowly. Most of the cells that we use today are variations on the Merrill Bassett design, which was, I hope I got this link right. I think this is the right, or the first reference to this type of cell in the literature. And there are lots of different types of cell. So I'm just going to flip on to the next slide and just check on my time how I'm doing. Okay. So this is what they look like. We have some tightening screws, we have a backing disc, we have a diamond, and then we have a gasket, and then that's mirrored on the other side. So we pull the diamonds together, so we sandwich them together like this, and in the gasket here we have a small hole with the crystal sitting inside it, and some high pressure medium is around the crystal to allow pressure to come in from all sides as the uniaxial force is applied. So our synergy system officially supports these cells here. So there's a small list here. That's not to say that other cells won't work. This is just the list of officially supported cells. And we will have 2 talks on these cells. So one is immediately after this presentation, and the other one is tomorrow, first thing. And these will be presentations on these offerings and other offerings from the companies that make these Diamond Anvil cells. So although they have all of these cells here and all of the ones that have been used in the past to do high pressure research, they have different bodies, but they use the same fundamental approach. And they all obviously have to be able to fit into the goniometer space, so onto the goniometer head and not collide with things as they're rotated around. So why do we use diamond instead of cheaper materials? And that's basically because they have several properties that are of value to us in this. So they're very hard. So they're capable of achieving the pressures that we need without breaking, although sometimes they even do break, depending on how carefully the pressure has been applied. They're optically transparent, so that means that once the sample is inside, we can align the crystal into the X-ray beam because we'll be able to see it through the diamonds. And that also allows us to be able to measure the pressure using spectroscopic methods, for instance. And we want to be able to get the X-rays in and out of the sample space, so the sample chamber inside. And thankfully, because these diamonds are made of carbon and they have a small unit cell, they allow a lot of the X-ray beam to pass through. We also need to measure the pressure. So we can do that with something like Ruby, but it can be anything that you have a known response to pressure, so you know the equation of state of the sample, and you co-mount that inside there with the sample that you'd like to do your X-ray experiment on. So this paper here will tell you a little bit more about how to do that. Generally, the idea is that we're using spectroscopic methods to optically see changes in the properties of that other material, and we can then find out what the pressure is using the equation of state. So normally, the amount of the pressure calibrant only needs to be very small. So to give you some idea of that, we have here a crystal inside a cell, and a tiny chip of ruby next to it. So if you're looking at this, so this is what it looks like under a microscope, and we're looking through the back of one of the diamonds into the sample chamber. So if I recall correctly, this is roughly a 200 micron gasket hole here. So we're looking at something like 70 by 70 on this copper acetate crystal. And the ruby here is maybe in the order of 5 microns or smaller. It's a bit hard to tell because we also have something here which is holding them to the surface of the diamond. It's a gel which sticks the crystal and the ruby. So there's a little bit of an optical effect from the gel piling up around the little ruby chip. So the beam on our synergy system is usually around 100 microns, depending on the wavelength. And this is about this size here in this image, and we're talking about full width, half maximum when I say 100 microns. So this means that most of the beam, except for very low intensity tails, will pass through the cell without any interaction with the gasket material. So it's clearly in our interest when it's like this to mount the crystal as close to the middle as possible, but we can also center on the sample like this. And when it's like this, as we rotate the cell, you might start to see some effects like the gasket being clipped by the X-ray beam, and that will lead to some diffraction. So again, I just draw your attention at this point to another talk on sample preparation. So we have one today at 9:15, so that's the talk after the next one. And that will be about preparing samples at pressure, I believe. So instrument considerations. So if you're interested in getting into this and you haven't done anything yet so far, you'll need to know a few things. So the Diamond Anvil cells are a little bit bigger than your crystal is. Although the crystal sample sizes are the same, we have this extra body around here. So this blue area is trying to show you how much space we need to have created in order to accommodate this cell. So there are newer cell designs which are smaller and can fit into the space without modifications. But generally we'll have to have an extended beam stop, which is something you can quite easily change just with a thumb screw, and shorter collimators, which we normally leave permanently mounted to make sure that we get the best performance out of the system. As far as the switching goes, once you have placed your high pressure beam stop on the system, when you start Chrysalis, if you have a high pressure setup, then you'll be asked this question and you have to make sure that you answer it correctly, because there is a small possibility that you'll drive the detector into the beam stop. But it's relatively easy and safe to select, yes, I have the long beam stop mounted, and I have it removed. So it will default to the safe option, and it's up to you to override it. So putting this metal cell onto the goniometer means that you're going to have orientations in which the cell body will block the X-ray beam. And we're looking at the sample through the diamond windows. So this is the primary beam coming in. And we're looking at it for both optical and X-ray purposes through the diamond like this. So it should be obvious from this picture that if you rotate too far, this part of the cell will come into the beam and block the beam from reaching the sample. And depending on the cell you're using, you might have something like an 80-degree opening angle. So that's this total angle shown here, over which you'll be able to rotate the cell around like this and still see diffraction from the crystal. So this body will also put a limit on the 2 theta angle, which you can measure diffraction to, and in turn the despacing that you're able to see, because we won't be able to see anything that diffracts at this angle if we're close to the edge of the cell here. So that means that long wavelengths like copper simply won't give you atomic resolution data, and shorter wavelengths are favored. So molybdenum is good for atomic resolution, as is silver. Another consideration that we have are that diamonds are crystals themselves, so they will diffract, and they will diffract strongly. So we'll sometimes see very high intensity reflections like this on our images. So we need some means to handle this, and that's the subject of some of the other talks coming up, which I'll highlight in a second. We also have in the sample chamber a crystalline, usually pressure calibrant, so you'll have some reflections. How do you know if these reflections are definitely from your sample or if they're coming from a piece of ruby that's too large, for instance? Then we have the hydrostatic medium in the sample chamber, which also can scatter the beam. And the high pressure medium is something you can't avoid. You need it there to be able to apply the pressure from all directions without crushing your sample. And depending on what that hydrostatic medium is, it can raise the background quite significantly or not so much. It will depend on what you've used and how soluble your crystal is and the various choices that you have. So this is usually not such a big consideration, but it is still something that you need to think about. The gasket material, which is used to form the sample chamber walls, is a metal, and that can often diffract and produce powder rings. So like you can see here, these are powder rings coming from a gasket with a large beam. And this is very intense. I think this was synchrotron data. So you can see that this is quite bad. And obviously we're going to have potential for overlapping sample reflections with these rings. So the upshot of all of that, and the point that I'm trying to make, is that when you do a high pressure experiment, you have lots of considerations that you wouldn't normally have for a standard experiment. So they can complicate everything from indexing your sample, collecting data, processing data, and applying corrections. And we need to consider and address each of those issues. And this auto movie is just showing you how bad things can get for a very messy and noisy sample. So I will go through the last few slides a little more quickly. So we have short wavelength as a preference for doing high pressure. You have to consider that molybdenum may diffract more strongly from your sample than silver. So it might mean that if you use silver, you'll have longer experiments, but generally silver will give you an improvement to your completeness and you'll be able to see higher resolution if that's of interest to you. We want smaller beams, so microfocus systems are now standard, and having a small beam is generally what these systems provide. So that's good. It means that you can avoid the gasket clipping the beam, so you can see the difference and the contrast between those two situations here. Not many gasket rings visible here, maybe just the hint of one here, and then here you have lots of them with a large beam. So experiments, I'll just quickly go through this because we have talks from my colleagues who will go over this in other lectures, but we need to provide that cell opening angle, and we also have some tricks for handling the difficult stuff like getting rid of the diamonds and overlap peaks. If you set up the opening angle, you'll get everything queued up automatically for doing high pressure experiments. So you can see here, hopefully, that we have a high pressure pre-experiment type, and that's your easiest entry point into doing a high pressure experiment. So in our strategy module, we also have consideration for these things. So again, this is what the opening angle is defined as. This is the half opening angle. So this is the number that you want to put into the software. In the majority of cases, I imagine that will be 40, but it depends on the cell that you've got. And we also have two situations that we can account for in the strategy as well. So one is to not tilt the cell. So that means moving it too much like this. If it's a very heavy cell, that can cause it to sag out of the beam. Or maybe you have some external apparatus connected to it which prevents you from moving it like this. And the other one is to not reverse the cell, which is this motion here. So again, if you have some like gas membrane cell, for instance, you don't want this type of motion to be happening necessarily. So cell shading, there are integration approaches to deal with this, and there are strategy implications for this. So I guess that Pierre will be talking about this in his presentation later on today to some extent, and there will be some consideration to this in the data processing and correction talks that are coming up later on, maybe tomorrow, I think. So we need to exclude diffraction from this region here with that. Indexing can be difficult because we have all of this extra noise. It's difficult to see where the periodic pattern is. We have some tools to help with that. So there's Eval Pro, and I think if this is not one of the things that's going to be talked about later on, we can show you that somewhere on the forum as well. And I have got 1 minute left, so I will skip through this because this is all going to be covered by the other presentations. So we have a talk from Jakob. I apologize for the slight formatting error here. So he'll be covering the Chrysalis Pro handling of a lot of these issues that I've just covered. And then tomorrow at 8:45, again, I apologize for the formatting problem here, we'll have a talk from Ross Angel on the theory behind a lot of these things and how what the approach is to handling them. And Ross is the author of the Absorb program, which does have some integration in Chrysalis Pro. So generating those files is quite straightforward from Chrysalis Pro, but Ross will tell you about the details of what you're doing and why. So I will stop at that point.